This morning, I had one question on my mind. How are CW keys actually made? I spoke with Aaron from Modern Morse, and the next thing I knew, I was touring his factory in St. Louis, Missouri, where every single Modern Morse key is handmade with precision and pride. What I had discovered was awesome, and you're about to see some of the process right here on Ham Radio Roadshow.
This is so basically designed this chassis to hold a bunch of different parts. These are pallets. I used to make things individually, one part at a time in a Kurt vise, but then once you sit there and you make one part, the machine runs for 5 to 10 minutes, and then you've got to turn around and do it again, so you're glued to the machine. This allows me to make, like, depending on what I'm doing, this will make 8 chassis for Op 1 at one time. So that takes about an hour to run. So now that I can stack a bunch of parts onto these pallets and then go run it, then I can actually walk away for an hour and go do some other task like building keys instead of being glued to the machine nonstop all day. So, and I have multiple pallets so that while one's in the machine running, I can be prepping another one, getting it set up so that way the machine, when I'm in production mode, the machine's not down for a long time in between cycles. So this one is kind of my jack of all trades palette here. And so what I've done is this is what it'll come out looking like. So this is operation 1, or I'll say op 1. These are for the actual tops that hold the top bearings and hold the plexiglass. And so basically this is called window machining. And this is essentially because you think like it's got a window frame, right? Or frame machining, however they want to say it. So like the back's not finished yet, but you can see the tabs that are left. That'll hold the part still in place. And then all I have to do after this operation is I literally just bend it and it pops right off. Kind of like a sprue for a plastic model.
Super cool.
Right?
Yeah, like
so we designed that into it.
old model car.
Yep, exactly. Yeah, exactly. So we're going to make some of these today. So I've already prepped this stock. So these are just flat 1/4-inch sheets of 6061 aluminum. I already have 4 holes drilled into it. I stack a whole bunch of them in the machine, and using a through spindle coolant drill, I'll just plunge through and pre-make all those holes. And then they're strategically placed 4 more holes here. And there's a bunch of other holes because I can do different fixtures on this. It's kind of like, actually the CAD model, I call this my Lego playscape. Like that, I literally named the CAD model that because I use it for all different stuff. Sure. So I got this on here, and then we're just going to throw in some 1/4-20 bolts. They're almost synonymous. You could call it a jig, a fixture, a pallet system. You know, there's different tiers of what you could call it. Versus the other side of that would be just like doing vise work holding, where you just got a vise, single axis vise that you're clamping and holding apart and machining, and then flipping it around the vise. This allows me to where I can do the work outside of the machine and then drop the pallet into the machine. Because if you look on the back side of these, these are called pull studs, and they self-locate. They have precision ground rings on the basically at the very top here, and then I'll show that to you in the machine. Inside the machine, I have this fixture, right? And so this fixture allows me to drop these pull studs in, and I tighten these side screws, and that basically pushes wedges in that will grab onto those pull studs, and it'll suck the pallet straight down, and it'll locate within 5/10 is the repeatability I've gotten out of this setup. And I machined out my own riser plate so that I could get this plate up. I bought this from a company called Fifth Axis Work Holding. I think they're out in California. So and that just allows me to rapidly change, and I'm not having to change out soft jaws all the time, right? So it could take me an hour to like switch out setups, and now I don't have to do that. Now I'll basically have operation 1 that I'm doing over here, and then op 2 that I'm doing over here. And then this is all set up for the chassis. And then if I'm done doing chassis for the day, I can immediately just drop a pallet on for the arms. And that's a really cool pallet. I'm really proud of that. This is a finished one. It's still got oil and some debris on it. I got to clean it off. So here, we're actually doing 3 operations at one time. So I start with billet block like this. This is 1/2-inch aluminum block. And that gets placed into each one of these spots. And then it gets clamped down with these pit bowl clamps. So these pit bowl clamps, basically, as you tighten down on the screw, it's got like a rocker arm, a cantilever, and it'll tighten in. And it'll only grab on about 70 thousandths of the material at the bottom, like 0.07 inches. Okay. And then that gives me room so I can basically machine the whole arm for op 1. And then I'll take, once this is done, I'll unscrew these, and then they get dropped into this section where we do op 2, and that's where we'll actually cut off that carrier plate, and we'll do a final chamfer on the top. This would be the side that you see when you're looking at the keys. And then to do all the side holes for all the contacts, there's a M2 screw, and then the press fit hole that we use for the 6mm magnet. That all gets done in this operation. What's nice is that this pallet, I hit the button once, and then every single time I run this, it'll do 4 sets of keys worth of op 1, 4 sets of keys for op 2, and then it'll do the third operation all at the same time. This whole pallet right now takes about 27 minutes. So about every 27 minutes, give or take, minus just quick changeover time, cleaning it off real quick, dropping a new one and hitting go. About every 30 minutes, I can get 4 sets of arms off now. This is recent. Like, this is something I started doing all of a sudden. Once I had to get my production up, I was making everything one at a time in a vise, and then having to switch over to making the left arms, and then doing a bunch of right arms, and then doing a bunch of left arms.
Does this also then improve on the accuracy overall?
I don't know if I'm not sure if this will improve on the accuracy. It just gives me better efficiency. And then it allows me, so part of like single piece workflow or within lean manufacturing, what I'm trying to do is make sure that I don't have a pile of one part just sitting there, because I can't make a whole key with just 100 left arms, right? I need all the pieces.
Yeah, okay.
So the whole idea here is I'm trying to do it to where I can complete everything. I can complete everything for this one part, right? 2 sides, each for a key. I can do that all in one push of the button, right?
Okay, yeah.
And then I'll still swap over, and then every single time I hit it, and then now it's remachining these, machining those, and then I always get, it's like a constant flow that I'm getting off there. So that way, like I said, I know if I hit the button on this 4 times, right, and I hit cycle start on this 4 times, I'll have 12 sets of arms for today, right? And then I know that then I can go through and do the Cerakote process, pull them out, and then they're ready to make keys. Before, the way the machine was set up before, I had to have to do a bunch of work to set up the machine to make one part, right? And so making that one part, and since there was so much setup time, you don't just make that one part and then spend an hour resetting up the machine, make another part, set up the machine, make a different part for the key. This way, I can do everything I need in one day to make like 10 keys worth of parts, right?
What are we doing next? Like, what's the next
So
step?
today, what I have the machine set up for is, like I said, we're gonna make a bunch of the tops, because I got to process these through in the second machine, because I need more tops, basically.
Okay.
This is for the production run for Dayton. So I'm going to tighten it up, and then I just use a failover torque wrench. So failover torque wrench, this is made by Vera, however you want to say that. The difference between this and like an automotive torque wrench, right? On an automotive torque wrench, right, you have a spring in it, and as you're tightening on the bolt, right, at some point it's going to click and almost like break free.
Right.
But then you could keep going if you wanted to.
Oh.
So like you could over torque bolts very easily, right? With an automotive torque wrench. With this one, it's got like a cam system. So as I tighten, you'll hear it click, and then it'll just keep moving. I cannot go beyond the torque that I set it to.
Okay.
So I make it what I call late night errand dummy proof.
Is there a certain pounds per square inch? Is that what you call it? When,
Sure. Yeah, the torque
is
specification
there
for
a
it.
certain specification for each individual, what I was calling a jig, each individual plate?
So part of the process when I'm designing one of these jigs, I'm looking for how much downforce that I need, and I don't want like how much clamping force, and also based off of the fastener itself, you know, there'll be a specification for the tensile strength of the fastener given a specific torque setting, because I don't want it to break free and like back out if there's any sort of vibration.
Yeah.
So I can look that up from the manufacturer for each piece of hardware that I use.
Oh, cool. Yeah.
So, and that's the big difference between like buying a bolt at Home Depot or something, or like buying it from some other source, is that, you know, like McMaster Car will actually send me the prints and everything that I need.
McMaster Car has some great stuff, and
Yeah.
you know, you go on there too, and they also have like STLs of all of their stuff too. So if you needed to make for example, I say a jig, and I keep saying a jig, but if you needed to make a jig, or you needed to base a 3D print off of that part, you could.
Oh, absolutely. You get the full 3D model, which I actually use because like this entire palette, this was all came from a 3D model. So I sat down in CAD, this whole thing, the block gets designed, 3D modeled up, even all the parts, all the Mighty Bite fixtures, all of that gets 3D modeled up so I can check clearances. And I can actually make sure, so like these fixtures here for these guys, if I show you this part, I'm missing a tool. Hold on. I will have to find that tool. So when I tighten down these screws, these little arms that expand with the wedge to hold these parts in, it only moves 0.010 of an inch. So like, I got to make sure that whatever I'm designing, I take into account that tolerance stack up. This was, because when I'm torquing things down, I was always like wrestling with this, like trying to hold it while torquing it. So instead, I just 3D modeled up this little fixture that I can set the part in and it gets held by the pull studs.
That's awesome.
And yeah, and that's one of those things where I needed the tool, right? And this is why I got into 3D printing. I got into it because I had a problem and I was able to sit down at the computer, 3D model this in about 10 minutes, and an hour, 2 hours later on my bamboo printer, I had the part I needed. And I bolted down to the table, problem solved. Move these. I only need to go about 300.
He found his hex bit.
Yep, I found the hex bit. It was right in front of my face.
It usually is.
Yep. And then these just pull right out.
Oh, okay.
And then these, oh, see, that's why I have that fixture over there. Just loosening up the pit bull clamps. These will then drop right in to that hole right there, or cavity, whatever you want to call it. Right? Drops right in, and then right now it can flop out, right? It can just come right out. And when I tighten down on the screw, there's a little like, I don't know what you call it. It's like a bevel, like inclined plane, so it tightens down on this little keystone, and it'll push these little sidewalls out to hold the part in place. With a remarkable amount of force, too.
Oh, yeah, there it is. I see.
Yep. So as I tighten, it'll actually spread those little arms out, and now the parts won't come out.
And for anybody at home who's wondering, maybe they've never seen a CNC before, this is oil right here. Is that right?
Yeah, that's just, leftover coolant from the machine.
Coolant.
Coolant, yeah.
Coolant.
It's an oil-based coolant, so it's about anywhere between 8 to 10% mixed. Like we get it in concentrate in a 55-gallon drum, and then that comes out. It gets sprayed over the whole parts. There's two reasons why we use the coolant with high pressure. One is to do what they call chip evacuation, which is as you're machining, you're wanting anybody that's ever done any sort of like, milling or even like with a Dremel, you're cutting and all of a sudden it's leaving swarf or extra chips everywhere. The coolant, as it's spraying onto it, will pick up those chips and wash them away.
Oh, yeah, that makes a lot of sense.
So chip evacuation is almost more important than cooling the tool. See this bin of chips over here?
I did earlier.
Yeah, so
it would not be fun to jump in that.
Oh yeah, I mean, I don't suggest people put, like if I ever challenge myself, I will. But you can easily, it's like I figured out after 15 years, there's a special way you have to like pat your hands when you get metal chips on them.
Oh really?
Yeah, because if you just wipe your hand, you'll dig a chip in and just cut your hand open. But if there's this like magic little machinist pat that will get the chips off and you can wipe them off easily.
We're getting all of them inside.
Apparently.
Okay.
So.
Yeah, wow.
So yeah, so the coolant basically will pull all the chips away, right, off the table.
Oh, to pull them away, okay, yeah.
Yeah, it'll basically wash it all away, and then it comes down to this. You'll see there's an auger down inside here. You see all the chips there left from another operation. So then I run that auger, and it pushes all the chips to the end and puts it in the bin for recycle. And then all the coolant gets recycled as well. There's about a 50-gallon tank underneath the machine here, so we're not wasting coolant. The coolant gets sprayed out, and you'll see it's flood coolant, so there'll be a lot of it. You can't hardly tell what's going on when you're machining because all you see is just a waterfall of white coolant.
Oh, cool.
And then it flows through it and goes through the tank. It gets filtered, and then it's a whole closed loop system. We lose a little bit to evaporation, and there's also you'll get a little bit that comes off on the chips, like the residue that you saw. So over time, we have to top off the coolant. Like I put about 5 gallons in this morning just to top off the tank. So. Yeah, they call that carry away. I think that's the official term because you're carrying away some of the coolant with the chips. So, because it dries on there as a residue. So these parts are actually, the material is extruded and it comes in slightly bowed. And I always want to make sure that the center of the bow is in the center of the part because the bolts will then pull down the rest of it down to the fixture plate because the height on this matters a lot. because if I'm machining and the parts actually, the stock is floating up too high, these little tabs are only about 17 thousandths thick. So if the part's slightly higher up, right, like if it was bowed, then all of a sudden those tabs wouldn't be there. There's no material there to cut, and then all of a sudden my parts are flying off the machine, and that's when you break tools and things get expensive fast. Just make sure there's no chips on the back. I'll drop right in there. So that's tightening in those wedges.
And basically, it's tightening both sides together.
Yep. So there's a left hand thread and a right hand thread. So it's tightening those wedges into place, and that's what's locking down those pull studs. So it's going to pull the tool out of the carousel, drop it just to your left, and then it's going to move it over using that dual arm, put it into the spindle. So. Here, watch. I'm going to switch to another tool.
Oh, that's cool.
No, you want to see it go faster? Hold on, here we go. That's a lot of metal moving real fast, in my opinion. So we're going to go to Toppers 111 P22. And we're going to go to the most recent one that I have. Select program, memory, graphics. I'm just going to double check that this is what so now it's running through the G code, and it's kind of rendering it in 2D over here just so I can see if it's actually doing everything. And it's actually executing all the code through the PLC to make sure that there's no weird movements or changes. You know, like I'm not telling it to go 400 miles one direction. It'll be like, you can't do that. And I'd rather figure that out now when I'm running a new program than like halfway through the program when the tool's in the cut. So it's just going through, and you can see, you can actually, I don't know if you can look in, you can see, so each one of those plates is going to produce 9 tops. So it's running through, it's making a little rendering of where it's putting holes and stuff like that.
That's cool.
So yeah, and it'll take just a couple minutes to run through this. Put it at 25% rapid. Oh, see? I'm going to let it get all the way down. I'm going to pause it. I'm going to hit stop, turn the coolant off. I'm going to turn this ball valve on. I'm now going to start it back up, and I'm going to go real slow because I just want to make sure I'm not. So I've gotten the part really close. The tool's really close to the part. I paused the G code, and then I'm going to come over here to distance to go. And it's saying the next command it's going to do, it's going to go down minus 0.25 or inches or about a 1/4 inch. And so if I look at that, if that number said like 3 inches and I'm right next to the part, then I know like I've done something wrong. Stop now.
Yeah, right.
So we might still.
Because at best you damage your plate.
Or the tool would break too. The tool would shatter.
Yeah, I was gonna say at worst.
Yeah.
Like catastrophic damage, right?
Yeah, I mean it would take a lot to damage the Z column on this.
Okay.
But yeah, I mean you can. In this case, I just don't want to wreck a $150 tool. If I go too long, it'll chip weld.
Doesn't it get hot too?
Yeah, very, very hot. Yeah, it'll produce steam. There's, I think, 6 tools total that it's got to go through to do this. So it's got a 1/2 inch cutter in there right now, which is decking down the plate. So it's making it uniformly flat with a really nice finish on it. That's a special tool there, so I get a nice surface finish. It's bringing that down to size, and then it's going to go in and actually cut out the middle, and it'll use an adaptive tool path to do that, or a tricoidal tool path. And it'll cut out the middle section, and then it's going to go in with a spot drill, a main drill, and then it'll do a boring drill operation for all the holes, just so that everything's perfect. There's no tapped holes in this operation, so I don't have to worry about that.
That's cool.
And then at the very end, it'll come in with an 1/8 inch end mill. It'll come in and it'll do that final perimeter, and it actually slowly ramps down so that you don't just bury the tool in a 1/4 inch of aluminum and then the tool, that tiny tool would snap. So I actually do almost like a helical ramp around the perimeter. So after I break it out of the tree, see it does have the tabs on it. And so then in this machine, this is the smaller Haas machine, I'll have this soft jaw set, die set, whatever you want to call it, right? Work holding. And so like it has these arms move in and out in a vise, right? Okay. So we've machined this out. The part will go in, this is the machine side, the part will drop in here and they get clamped into place, right? And so now it's pinching on the sides, and then we actually go in and we deck this off with a large cutter and then actually finish and chamfer all the holes. So it gets machined on all 6 sides of the part.
And that basically gives it a, can I touch this?
Yeah, sure.
It basically gives it like a smooth finish, essentially.
Yeah, here's a finished one. So you can see the difference. So like, that's one that would have been finished machined versus a rough one.
Oh yeah, you could tell there's a more shine to this, right?
Yeah, yep,
and like
exactly.
if I touch it, I don't feel like it's like grabbing, or you know, like with this one, it's like I can feel how it's a little rough.
Yeah, this is
raw
nice
stock
and smooth on this side.
Okay, cool.
So and then we actually so we machine it on all 6 sides. Well, I mean it's only 2 operations, but you know we're decking the top, putting all those holes in, and then flipping it over and finishing the backside.
I have an amazing question for you that I've never heard anybody tell me before, and I came up with it completely on my own. But why don't you just sell these aluminum bare metal?
Right? Yeah. Okay. So aluminum likes to scratch really well. I mean, it just does. And if I were to just sell one that's bare metal, within, you know, just throwing it in your backpack or whatever, it's going to have a whole bunch of scratches on it. On top of that, bare aluminum, like 6061 aluminum, that's exposed to just ambient atmosphere will begin to rust, or it produces an oxide layer. That's what rust is. So it produces an alumina oxide layer, which basically doesn't conduct any electricity. And we need to be able to move current through the chassis to make connection for the key. So if we left it bare by itself, or with no like deox type oil on it, for the areas where there are threads that we want current to go through, it would basically rust, and then it wouldn't work. The key wouldn't work after a while.
Or intermittent connection to the point where you're like, what's going on?
It would drive you nuts.
Yeah, totally.
Yeah. So
cool.
And I like the colors.
That's awesome. Yeah, colors are always good on a key, right?
And people will ask. There's other coating methods, but oh, it's aluminum. Why don't you anodize it? So anodizing actually artificially produces that oxide layer, and like it almost looks like a honeycomb skin that gets grown onto the layer at a microscopic level, and then dye actually fits in. Yeah, so that's anodized.
Yep. And so you're saying, like with anodized though, this wouldn't be conductive.
Yeah,
right?
It should not be conductive. We
Right.
can actually test that. We'll take it back to an ohm meter. Find something that's anodized, and if you put an ohm meter to it, it shouldn't
See
have
if there's continuity, and if
Yeah.
there is, it's not properly anodized or whatever, but
Exactly.
right, yeah, okay, that makes sense, cool. So that's why you don't do the anodizing, is that right?
Yeah, because I want to maintain the conductivity at the surface level where I'm making contact, and I also have a more consistent. It's a more consistent process, because anodizing, there's so many variables involved. There's how long it's in the tank for, how much current you're using, what the surface area is of all the parts. So every single time I've sent parts off to anodizing, I never get a consistent color back.
Yeah.
And so I want to standardize, and Cerakote does that for me.
Well, if you Cerakote it, there's continuity then, and you said no, there's not continuity, but all you have to do is, did you say block off these holes essentially?
Yeah, I could just block those. I can block off the threaded holes, especially like the bearing holes where current might be traveling through those. If I anodize this, then there would be no continuity there, and the key wouldn't work.
Makes sense.
So for Cerakoting though, I can do that, and it's easier to mask it because it's not like a dunk process in a tank where the liquid's going everywhere. Instead, this is like a paint-on 2-part epoxy process.
So I'm going to build my own key now, and what I need to do is I need to grab 2 of these and 2 of these, because you got like lefts and rights or vice versa, and so you can't just grab 4 of these and hope that they're going to fit. I mean, you can, but good luck. And eventually what it might end up looking like is kind of like that, but let's go check it out.
This is just the CNC process, where raw aluminum becomes the key's core components. But there's more, like in-house PCB design and fabrication using Modern Morse's own pick-and-place and reflow machines. Precision meets modern tech, all under one roof. The first thing I'll do is pop out these little silicone plugs. With those plugs removed, I take 6mm bearings and I'm going to put them into where we just popped out those silicone plugs. In this step, not having them perfectly aligned or flush is completely okay. A small piece of cylindrical brass is used as a persuasion tool to help guide those bearings into the correct spot. Next, we want to use magnets to help repel the arms, and so we're going to take a 1.5mm hex tool and we're going to insert into the case. We're then going to take our 1.5mm magnets and we're going to place it on the hex tool and basically regress it back out so that it threads into the chassis. Next, we drop in the PCB. Now, it's not making dits and dahs, that's your radio's job, but it does make sure that the paddle signals will get from your fingers to the rig cleanly. It handles the wiring to the output jack and it keeps things smooth, stable, and static free. Now I'm adding the center isolator to the PCB, using an M3 screw to lock it all in place. First, I thread the screw into the isolator and then I carefully align the pin with the PCB. This keeps everything centered so that it won't wobble when you tap the paddles. I tighten it down snug and 2 M2 screws apply just the right amount of pressure to the contact pads, ensuring solid, consistent continuity. And a quick check with the multimeter confirms we're good to go.
And then the other side, just to make sure.
Yep.
And also, I always check to make sure, like, somehow continuity didn't jump between the two.
And that can happen if, for instance, somehow, luckily on these printed circuit boards on the back side, we don't have, my dad helped me design that. And one of the principles he absolutely wanted to adhere to is to make sure that we actually had no signal traces on the bottom side of this PCB, because if for some reason the solder mask were to wear off, we didn't want it to short to the chassis.
Yep.
Now we're working with some really tiny parts. 2 Delrin balls. These little guys drop into the slots just above the magnetic returns. And I start by slightly sandwiching each ball into those slots with an M2 screw, just over finger tight to press it down into the threaded slot. Then comes the magic. A second M2 set screw goes into the same thread and pushes against the Delrin ball. That first screw helped us get enough pressure since you never get the torque needed with just the set screw alone. And with that, the main part of the chassis is nearly complete. Next up, we're adding the arms to the key. Now, Aaron at Modern Morse already handled the tough stuff, installing the magnets and the pins, and I get the easy job. I start by threading these screws into the arms just about flush, and this helps keep everything consistent during assembly. We'll fine-tune them later once the key is nearly done. I do the same thing with the left arm, but now I need another Delrin ball and an M2 set screw. Yep, more tiny parts, and I may have lost a couple, and Aaron casually reminds me that, hey, they cost $50 each. Jokingly, of course. I hope. Once the Delrin balls are in place, I thread in the M2 set screws, and these help lock everything in so that the contact screws don't slowly twist themselves loose over time. Next, we're installing the tap handles on each arm, and thanks to Aaron's clever use of CAD or computer-aided design and a 3D printed alignment guide, this step is a breeze. The guide makes sure every paddle handle lines up perfectly, no guesswork, just precision. And honestly, it's pretty cool to see 3D printing used to dial in this kind of craftsmanship. This is starting to look like a key. We're going to take our arms now, and we're going to place these small washers on the pins, and we're going to place the pins into our bearings. And of course, I'm going to place the arm into the chassis where the bearings are. It looks like this, and of course, I'm going to play a little bit and tap it. Nice. At 10,000 likes, I will go back to Modern Morse and ask him questions that you might have in the comments below. I place the other arm into here, and of course I'm just playing around now to see if it has action and if the magnets are responding, and everything seems really cool. I'm excited. The next step is to place the cover on top of the key. Of course, I can't put the cover on the top of the key until I put 2 more washers on the pins like we just did on the bottom. And who am I kidding? I'll settle for 1,000 comments. Just leave a comment below. The top cover is only going to go on one way. And by the way, that plexiglass on the top cover is also made in Aaron's factory.
One process we didn't get to see today, and I think that I know this is the plexiglass that you cut.
Yeah, we cut that on a laser here.
Super cool.
What can I tell you? All we have to do is put these 4 M3 screws in, and of course we're going to later on adjust what I call the action, or the play of the key, if you will, and make sure that everything is completely functional, which I did confirm, and I was really happy that it did function correctly. I'd like to thank Modern Morse for having me out to St. Louis, Missouri, where I got to tour this factory on the Ham Radio Roadshow. And it's always been a dream of mine to be able to tour a factory and to see how things are made and to push my knowledge while learning from others. I wish I could tell you I had all the time in the world to be able to go out and test this key in the field, hang out with Aaron for a few hours, and I hope to return soon. And I hope that there's more opportunities to be able to learn cool stuff like this and be able to show you the experience of building a CW key. Ultimately, I hope this motivated you to continue to pursue knowledge. Thanks for watching the channel. Have a good one, and 73.